Hey guys, my name is Pedram, and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, now that we know what are different types of machine learning algorithm and how do machines actually learn, it is time to explore different machine learning models. The first one that we cover here is linear regression model. So part 11, linear regression in machine learning. Here's a roadmap for different machine learning algorithms and models that I'm planning to cover for this conceptual crash course. Later on, I may add some other models if I see there is enough demand for that. Okay, so let's start with our supervised algorithm. And the first model is going to be a regression model. We start with the very basic one, linear regression model. Okay, so what are the linear models? The linear model is an important example of parametric model. If you remember from our previous parts, we talked about what is parametric versus non-parametric. Parametric models were the ones that we are not imposing any functional form, any restrictions to the model, right? So for example, in simple linear regression, we had something like this, y is equal to beta 0 plus beta 1. This is in econometric language. x1 plus beta 2, x2, and etc. Plus some noise or unobserved factors, right? So we are imposing some linear structure to the model because we are imposing that f of x to the model. We call it its parametric. Okay. So in linear regression model, we have a collection of labeled example because as we said earlier, it's supervised, right? So we need to provide both x and y's, inputs and output to the model. And n is the size of the collection, basically size of the our sample size, and x is a d-dimensional feature vector. So for example, if you're trying to predict what is wage, and the features can be experience, education, gender, age, and etc., right? It's a d-dimensional vector, and y is our real valued target variable. Because remember, we were talking about what's the difference between regression versus classification. If the target variable is real valued, is continuous, we call it regression. Now let's rewrite this simple linear regression model in its machine learning format, machine learning terminology. So in machine learning, we show the betas, or with W, we call them weights, and this B that we used to call it intercept in econometrics, in machine learning, we tend to call it bias, okay, the constant or the bias term. And we can summarize this function as f of W and B. This is the thing that the machine is expected to learn, right? The machine is expected to come up with an estimated version of this pattern in the data, and it's going to do that by solving for the weights of the features and the bias term. Okay, and so f of W and B is a linear combination of features and parameterized by W and B. Remember, these models are called linear because they are linear in parameters. So as long as the model is linear in parameters, so we have, for example, W1 x1 plus W2 x2 and etc. As long as the model is linear in parameters, we call it a linear model. So for example, if I have here to the power of 2, or if I have interaction between x2 and x3, these are still perfectly linear model because the model is linear in parameters. All right, our W, the weight matrix, is going to be a d-dimensional vector of parameters, and B is a real number. All right, our linear model is going to be specified with d plus 1 parameters. Why? Because remember, this weight matrix is going to be d-dimensional because we have d features, and we need to estimate also this bias term as well. So the model needs to estimate d plus 1 parameters. Okay, we estimate the parameters w stars and b star by fitting the model to train data. So imagine this is the entire data set. As we said earlier, we're going to discuss, split it into, let's say, 80% train set and 20% test set. And the model is going to learn the parameters of the model, namely W stars and B star, using the train set. Okay. Then, although it is almost never correct, but a linear model often serves as a simple and interpretable approximation of the unknown true f of x, right? So remember, guys, at the end of the day, we are trying to estimate this true relationship in the data, but we know that it's unobservable. And linear regression model is going to be a very simple model, and most importantly, it is interpretable, because you can perfectly interpret the weights. These are the loadings or weights of the features, right? So for example, if the weight for feature 1 is W1, we can perfectly interpret this one. All right. So one of the big advantages of linear models, linear regression models, is that it's simple and interpretable. And it may seem overly simplistic, but remember, linear regression is extremely useful, both conceptually and practically. So this is one of our simplest machine learning models that has huge application because of its interpretability. Because remember, sometimes even in machine learning, you're still interested in being able to interpret things. So linear regression models rarely overfit. So what do we mean by that? So look at this example. So here we have, imagine this is the true relationship are these blue curve, right? So the blue curve is the true relationship. If you use a linear regression model, a linear model with a linear fit, right? So this is linear fit, right? This orange line is our linear fit. In this example, it is obvious that it's not going to overfit at all, right? But if the model is linear, but the fit is nonlinear, so this is nonlinear fit. Again, in this example, as we can see, it's doing a perfect job and it's capturing the true relationship in the data without specifically overfitting the data. And then the third one, the model can be linear, but the fit can be nonlinear as well. So this is again another, let's call it complex nonlinear fit. In this example, this orange curve is capturing noise. It's not capturing the true relationship in the data. Basically, it's memorizing from the train set. And obviously, it's overfitting here. So linear regression models, guys, in this example, all of them are linear. But because we want to keep this linear regression model mostly interpretable, we are not going to make it super complex like what we have here. So in general, when we talk about linear regression models, at most we have the quadratic version of the features in the model, and that's it. And we keep it very interpretable. And for that reason, if we stick to a linear fit or a nonlinear fit like this, it is going to rarely overfit our data. Now let's talk about the fact that in linear regression models, how do the machines learn the pattern, learn the code, and basically find the W stars and B stars? So here is our optimization problem for the linear regression model. We are basically minimizing the mean squared error over some parameters of the model, namely W's and B, right? So this is the definition of mean squared error. We are saying this is residuals error y minus y hat, and we square them and we take the average. So this is our mean squared error. And if we can replace this y hat that the machine is going to estimate by this function f of w and b xi, right? So this is what we call the objective function, or in general loss function or cost function, right? So in all those machine learning models that I show you in the first page, we are going to introduce a specific loss function. Not necessarily all of the models, but most of the models have a loss function. And the goal for the computer is using one of those solvers that we talked about earlier to figure out what are the optimal values of parameters, right? In this example, our loss function is a squared error loss. So here I have a question for you. Why we are using quadratic loss function? Why not using absolute value or cube? So why we don't do something like this? So for example, absolute value of y minus y hat, summation, or summation of y minus y to the power of 3, and etc. So what do you think? Yeah, as you may have guessed, the answer is it is more convenient to work with a quadratic loss function. Why? Because it is well behaved. And by well behaved, I mean it's going to be continuous, and there's derivative at every single point, so it's well behaved. And also there exists a closed form solution. We know that from our econometric, I assume that you have a background in econometrics, and from the econometrics course, we know that there's a closed form solution to this optimization, and we call that engine OLS, right? Ordinary least square. And we could calculate the coefficients of beta hat using this formula, x prime x inverse x prime y, right? So here we are calculating the weights. We just renamed the betas by weights, and now we can either use OLS or use gradient descent. So maybe here's a difference between what we do in econometrics and what we do in machine learning. So in econometrics, we always use OLS or some other engines to estimate the parameters. In machine learning, we can use gradient descent as one of the solvers to solve for the parameters W star and B star, right? And because this loss function is very well behaved, you must always get the same answer. So it really doesn't matter if you use OLS or if you use gradient descent. All right, so now that the model has been trained using the train set, and the machine was able to find the W stars and B star, either using OLS or gradient descent, it is time to make some estimation in the test set, right? It is time to calculate for those Y hats, make some predictions. And with those predictions, we can compare the model performance by using some evaluation metrics. So one of the most common evaluation metrics that we use for regression is R-square. And it is defined as the explained part, sum of square of explained divided by sum of square of total. And I assume that you have some basic backgrounds in econometrics, so I'm not going to talk about the details of these formulas. And I assume that everybody here is familiar with the concept of R-square. But we know that there's a caveat with this formula for R-square, right? Because as long as, so let's say this is my Y variable, the target variable, and we're regressing it on X1, X2, and etc., right? The caveat is that we know as long as these variables that you're adding to the model, as long as they're relevant, basically there's correlation between them and Y, your R-square is going to decrease no matter what. So this is a problem, right? Because you don't want to keep some random variables on the right-hand side and get a better R-square. So what should we do? We're going to use the adjusted version of R-square. So we call it adjusted R-square, and we're going to do something like this. We say, okay, if K increase, then R-square is going to also increase. Then we have to look at the net effect of that increase in K, right? So if K increase, this whole thing is going to decrease, right? Because when R-square increase, this whole thing decrease. And the denominator is going to, on the right-hand side, is going to decrease, so the whole thing is going to increase. At the end of the day, we have to compare this effect with this effect, right? Let me use other colors. If K increase and the 1 minus R-square decrease a lot compared to a slight increase here, then what will happen? The adjusted R-square is going to increase. So adding that extra variable was beneficial. So we're going to go ahead and add that variable. However, if you add a variable and the R-square, let's say, decrease, but this right-hand side increase more, then your adjusted R-square is going to decrease. So it was not beneficial to add that right-hand side variable. So this is the adjusted version of our evaluation metrics R-square. What other metrics do we use in regression? So the other metrics, the one that are commonly used are mean absolute error, basically looking at errors, the absolute version, and take the average, mean absolute error, mean squared error. So this is basically, we talked about it in our loss function, and also the root mean squared error. So this is, we take the square root because the unit of root mean squared error is the same as the unit of the target variable. Okay. Then we can think of the adjusted version because we have the same problem here. Here we know that if I add some random explanatory variable, some random features to the model, let's say xk, then RMSE is going to basically decrease no matter what. Because when we add explanatory variables, more explanatory variables, the errors are going to decrease, right? So this thing is going to decrease. All right, so what are the adjusted version for the RMSE or MSE? Well, we can use something called AIC and BIC. So AIC stands for Akaike Information Criteria, and BIC stands for Bayesian Information Criteria. The idea of these two statistics or metrics are pretty much the same. We are basically looking at the function of k. K is the number of explanatory variables or number of features, minus a function of likelihood, right? So again, a function of k minus a function of likelihood. So what is likelihood function? We show it with L hat. And later on in logistic regression, I'm going to talk about the details of likelihood function. But for now, just think about it like this. What is the probability that the true data, the true observations are coming from the model that you're specifying, right? So what is the probability that given the values for parameters? So we say that, okay, given the values for W and B, what is the probability that the data is coming from this model, let's say this linear regression model, right? So most probably it is obvious that you want to maximize that probability, right? So if you want to maximize that probability, you would better to minimize the negative of that probability, right? So in general, we always want to minimize the AIC. When you compare different models, you will pick the model with the smaller AIC. Now let's see how it's going to adjust for the fact that when you add more explanatory variables, it has to penalize that statistic somehow. So here, as I said, the idea is simple. It's going to have, look at that. If k increase, this part is going to increase, right? So both for AIC and DIC and BIC, right? So we know that if you want to minimize this thing, so we have to keep it in balance, right? Because this thing is going to increase, yes, and yes, the probability of likelihood is going to also increase, and so the negative version is going to decrease, right? So again, as we discussed it in adjusted R-square, here for AIC and BIC, there's a trade-off between the two, right? So we have to see which effect dominates. And that's how AIC and BIC are penalizing adding K, adding more explanatory variables to the model. All right, but I want to talk about something that we do in machine learning. Now, if you notice, in machine learning, we rarely use these metrics, adjusted R-square, AIC, BIC, and etc. And there is a reason for that. And the reason that we use these metrics, these adjusted versions in econometric is that usually in econometrics we use a train set and we look at the performance of the model in train set as well. Because in econometrics, we are mostly interested in being able to tell a story. We are mostly interested in the interpretability of the model. What are the coefficients? Are the coefficients significant or not? And etc. etc. Right? Yes, if it is time series, we look at out of sample versus in sample. But in general, in econometrics, we have one sample and we report the performance metric in that one sample. So for that reason, we have to work with the adjusted versions of the metrics. However, in machine learning, we have train set and test set, right? So here is our train set. Here is our test set. And at the end of the day, we are comparing the models by looking at their performance metrics in the test set. Or, now that you know what is the idea of cross-validation, it is better to use report the performance metrics in the cross-validation set, right? Which is built on top of the train set. So for example, so what do I mean? I say that in machine learning, when you're calculating the RMSE, you report the RMSE of the cross-validation set or cross-validation version, or you report the RMSE in the test set. In either case, this is going to automatically control for the factor that we are not overfitting. Because we know that if you overfit the data, the RMSE in the test set or the RMSE of the cross-validated version is going to explode, right? So it's as if using the performance metrics in the test set or the cross-validated version is going to automatically do that adjustment for us. So I don't need to report the adjusted R-square in the test set. I don't need to report the AIC in the test set. In regression, when I do RMSE in the test set or cross-validation version, it is automatically controlling for that fact. And it's automatically help us to avoid overfitting using our linear regression model. All right, That's pretty much it. Now let's conclude this part with going over the question of the day. All right, so we have seen this meme before, you remember? So why don't you let me know what you think of what's the point of this conversation? Okay, so write your answers in the comment section, and until the next part, stay safe and see you in the next one.